Ladies and gentlemen, welcome to lesson 5.4. We are going to be learning about factoring quadratic expressions in the form x squared plus bx plus c. But before we do that, we want to quickly review the types of factoring, the strategies of factoring that we have learned so far. So you have a little bit of space at the top of your page for review. I'm just going to write two very quick examples. They're very similar to the homework we just went over. But the first one has to do with find a common factor. So always when you get a quadratic expression that needs to be factored, or any kind of expression that needs to be factored, look for a common factor. It's the easiest way to do it. So for instance, we're given the quadratic expression x squared plus 4x, and we want to split that into its factors. What's the common factor between the two terms, 6x squared and 4x?
2.
Numerically, we've got a 2,
X.
and the variable, we've got an x. So we pull that out. Then we have still two terms. We still are going to have a binomial inside our brackets attached by addition, just like it is out here. But we do 6x squared divided by 2x. So we're essentially pulling the 2x out of 6x squared. We're going to be left with 3x. And we're going to do the same thing to 4x. We're going to divide it by 2x, which is going to leave us with 2. And I could double check my answer by multiplying back. 2x times 3x is 6x squared. Yep. 2x times 2 is 4x. Yep, good to go. The other strategy we need to be familiar with is factoring by grouping. So if you were given something like x squared plus 3x plus 2x plus 6, where we can look at all four of the terms and we find no common factor that we can pull out of all of them, then we can simply group our terms. I notice that these two terms have an x in common, and these two terms have a factor of 2 in common. So over here we can pull out x, which leaves us with, Isaiah, what's going to be in this bracket?
X plus 3.
Nailed it. And over here I can pull out 2. And Julia, what's going to be left in that bracket?
X plus 3.
X plus 3. Well, now we can see that we have two terms still, this term with 2 factors and this term with 2 factors, and they share a common factor, don't they? They share a common factor of x plus 3. X plus 3 is getting multiplied by x, and it's getting multiplied by 2. Done. And again, I could double check my answer by simply distributive property, foiling this all out, and I should get x squared. I'll get plus 5x at the end, plus 6, to show that it's true. Okay, using the space on that page wisely, we're going to take some notes. The first note that we're taking is simply on quadratic expressions. Quadratic expression, what is it? It is a second degree polynomial. So we learned that we can name our polynomials after their degrees by the highest power of the variable. So a quadratic expression is always going to be a second degree polynomial. That means whether the variable is x or t or w, doesn't matter. It can only ever be raised to the power of 2 as its highest power. There could be another term that's raised to the power of 1, that's fine. But there can't be another term that's raised to the power of 3. Does that make sense? The highest power is going to be the power of 2. And we can do a couple of examples here. So that means something like 4x squared plus 20. That's a quadratic expression. The highest power of x is 2. It's an expression, not an equation. Why isn't it an equation? Expand on that answer. Vlad says it has no y. Where would the y go if it were an equation? It'd go on the other side of an equal sign. An equation needs an equal sign. There's no equal sign here. It's just an expression. It's just like a mathematical statement or sentence. It's just an expression, not an equation. Another example of a quadratic expression could be x squared plus 7x plus 10. How do we know that's an example of a quadratic expression?
Highest degree is 2.
Highest degree is 2. Yeah, highest degree of the variable, the exponent, is 2. Go ahead and write a third example of your own. Good? Okay. Make sure that your example is the highest, has the highest degree of the variable is 2. Could be adding or subtracting in here. Doesn't matter, as long as there's no x to the power of 3 in it. And there must be an x to the power of 2. If there's only an x to the power of 1 in it, like that term, and that term is gone, then it doesn't count. Another note that we need to have is the difference between factoring and expanding. So we've done both of these things now, but basically I'm going to give you an example of a trinomial, a quadratic expression. It's x squared plus 4x plus 3. And I'm going to give you the exact same quadratic expression in factored form. Don't want to use that color. When we go from the trinomial to the product of two binomials, it's called factoring. When we go from the factors to the expanded trinomial, it's called expanding. Now, what strategy do we have to expand two factors? How can I get from this two factors side, factored form, into standard form? Yeah, we just use our distributive property. We use FOIL and all those other patterns that we know. Today we're going to talk more about how to get from the trinomial to factored form. We did it a bit yesterday, right? We pulled out common factors and we factored by grouping. Today we're going to learn a different strategy for situations where those two strategies don't really work. Okay? Okay, so we know that a quadratic expression can be factored. Lots of them can be factored. But how do we know what those factors are? How can we figure out the factors if we're given a quadratic expression, a trinomial? Let's draw a few and see. So we're going to take the same one we've been dealing with. We're going to take x squared plus 4x plus 3. And I'm just going to draw it as algebra tiles. So basically we would have, maybe I'll show it as, I'll show it as algebra tiles. So we've got x squared, and we have 4 x's. So I know in this grid there's going to be 4 x's, and there's going to be 3 1's in this bottom area. How could I get 3 1's? Is this going to be a box, a 2x2? How am I going to collect my 1's here? 2x2 would get me 4 1's. I only have 3 1's. So my only option is 3 right in a row. And that shows you that you're going to have an x here, an x here, and an x here. And you're going to have an x here. Now that's still just our expression of the product, right? That's the expression of the product. How can we find the factors? Well, it's easy from our perspective because we can see that this side length has a length of x. This side length has a length of 1. This side length of x squared has a length of x. And these guys each have a side length of 1. So using algebra tiles, we have a rectangle representing the product, and visually we can split it into its factors. So in factored form, this product can be expressed as x plus 1, that's right here, times x plus 3, that's right here. Let's try another one, but instead of using algebra tiles, we'll just draw a simple grid. Okay? So in our second example, we're going to do x squared plus 6x plus 8. And we're going to draw it as a box. We don't know much about the box except that it has x squared in it, right? Now we know also that our x's are going to go here and here, just like in our algebra tiles, right? Our x's are in these corners. And our 1's are going to be in this bottom right corner. Well, how many 1's do we need? We need 8 1's. How can I arrange this in order to get 8 1's? It's going to be a 2x4 rectangle, and it doesn't really matter which side gets 4 and which side gets 2. It doesn't really matter. But all I know is I'm going to have 8, and it's going to be a 2x4. So I'm going to go with 4 there and 4 there. Now what does this tell me about the location of my x's? How many are going to be in this area?
2.
There's going to be 2x here. How many are going to be in this area?
4x.
Yeah, 1, 2, 3, 4. There's going to be 4 x's.
There's 2 little boxes. See?
Do my x's add up to 6x?
Yes.
Yep. Do my 1's add up to 8?
Yep.
Yep. So now all we have to think about is that in factored form, the trinomial is the area of the rectangle, and the factors are really just the length of this side and the length of this side. So the length of our top side here is x, and how many x's? We have 4, right? So here we have x plus 4, x plus 4, and here we have x plus 2. And that's the answer in factored form. So what we learned from looking at algebra tiles and looking at the grid is that the quadratic expression, and you might want to put in like a box or a star beside this, the quadratic expression is like the area of a rectangle. It's like the area of a rectangle. Factoring a quadratic expression is like finding the dimensions, the length and width, the dimensions of that rectangle. Okay, so we have any old rectangle and any old quadratic expression. Let's just take the general case, x squared plus bx plus c, and put them in a rectangle. Then factoring that quadratic expression is like finding the dimensions of the rectangle, where each binomial that gets factored, or each piece that gets factored out, is like either the length or the width of the rectangle. Because length times width equals area, right? So one factor times another factor equals the quadratic expression. And that's what we just kind of looked at with algebra tiles and the grid. Another way that we can think of factoring quadratic expressions in this form is to study the patterns that we learned when we were multiplying binomials. So when we were distributing, we learned a few patterns, right? If we had a plus b squared or a minus b squared or a plus b times a minus b. We had patterns that would work with. Now we're kind of doing the same thing but backwards. So let's look at what happens if we use a pattern. Let's take x plus r times x plus s. Now this just represents any factored form polynomial in the whole world where r is some number and s is some number. Okay, does that make sense? Well, if we used our distributive property on this, we'd end up with first times first, which is x squared, outside times outside, which is s times x, inside times inside, which is r times x, and last times last, which is r times s. What do these two terms have in common? They have x in common. They're both x's. So if we were to FOIL another one, like with numbers, and we got like 2x plus 5x, what would we do with those x's? We'd add them up and say this is 7x. Well, we can do the same thing in our general case, except we don't know what s and r are. So we're going to leave it as this. We know we have whatever added up s plus r is, s plus r, that's how many x's we have. So we have s plus r times x. And at the end we have r and s. Let's look at this carefully. What is the connection between the first term in the trinomial and the stuff here in the binomials, the product of two binomials? What's the connection? It's just the first thing squared. What about this third term? What's the connection here? It's just last times last. Last times last. R times s. So it's the second term of this binomial times the second term of this binomial. What about this middle term? What's its connection?
Just the second is the r in the first one times the second one, or the second one.
Yeah. We're just adding up our two numerical values, right? We're just adding up the second terms in each binomial. Just add them up and times them by x. So if we look at our r and our s, okay, the coefficient of the x term, that means just the number that's in front of the x term, is the sum of s and r. So the coefficient of the x term is the sum of s and r. And what's this called? If you times s and r, what's that called? When you multiply things together, the answer is called the product. So this is the product of s and r. That's a connection that we're going to be making as we learn to expand and as we learn to factor. So we're going to head off to example 1, and we're going to use this strategy, which is actually called sum and product. We're going to find the sum of the middle terms and our product to get our last term.
Let's see how it works.
Okay, ladies and gentlemen, we're heading off to example 1. Example 1. And the instructions here are factor if possible. So if we take a, which is x squared, by the way, there's going to be 5 examples, but you also have space on the back page. So don't worry too much about running out of space. You have x squared plus 7x plus 12. Now, from the notes that we just took, we know that we should compare this to the form that we're working on. So if I compared this to our basic form, where we have x squared plus bx plus c, then what is the value of b? b equals 7. What is the value of c? c equals 12. Now from the other notes that we just took, we know that once we get down here into factored form, x plus r, x plus s, I'm not going to do this for every example, we'll just do it for this example so that you have it step by step and everything explained. I know that the sum of r and s is going to make up the coefficient of that middle term. So r plus s is going to be equal to b. And what's b? 7. So the sum of r and s is going to be 7. Now the last term of my trinomial is built by taking r and s and multiplying them. It's built by getting the product of r and s. So c is the product of r and s. Well, what's c in this case? 12. Okay, I don't know what r and s are yet, but I've just shown that whatever they are, they need to multiply to 12 and add to 7. Does that make sense? Because they have a product of 12 and a sum of 7. So let's look at our factors of 12. What could the numbers be? Two numbers that multiply to 12. Could be 2 and 6. Could be 3 and 4. Any other numbers?
12 times 1.
Could be 12 times 1. Hey, what about negative 2 and negative 6? Do they multiply to positive 12?
Negative 4. Negative.
Negative times a negative is a? So that means we've got negative 3 and negative 4. We also have negative 12 and negative 1. Okay, of these pairs, which pair, which set of numbers has a sum of 7? See that? So 3 and 4 are the only two numbers that will multiply to 12 and add to 7. Right? 2 and 6 have a sum of 8. 12 and 1 have a sum of 13. Negative 2 and negative 6 have a sum of negative 8. Negative 3 and negative 4 have a sum of negative 7. Negative 12, negative 1 have a sum of negative 13. 3 and 4 are the only ones that have a sum of 7. So I know now that r and s are 3 and 4. X plus 3, x plus 4. And you have just learned how to use sum and product to factor a quadratic expression. Example 1b. b is x squared plus 4x plus 6. Okay, right away I'm going to go over here into my sum and product. What do r and s need to add up to?
4.
Yeah, the coefficient of my x term. They need to add to 4, and they need to multiply to 6. Every time we make this list, you're going to start in the product column, and you're going to identify two numbers that have a product of 6. Emma, can you give me two numbers that multiply to 6? 2 and 3. Vlad, any other ones?
6 and 1.
6 and 1. Jonathan, any other ones?
Negative 6 and 1.
Maybe negative 6 and negative 1, yep. And the last one? 5 times 1 is 5, so that one won't work.
Negative 2, negative 3.
Negative 2, negative 3. Now, do any of these have a sum of 4? 2 and 3 have a sum of 5. 6 and 1 have a sum of 7. Negative 6, negative 1 have a sum of negative 7. Negative 2, negative 3 have a sum of negative 5. Can this be done?
No.
So since no two integers have a product of 6 and a sum of 4, this trinomial cannot be factored over the integers. Cannot be factored over the integers. That means you can't break it into its factors using whole numbers, positive or negative whole numbers. It could still happen. There could be decimal numbers that will multiply to 6 and add to 4, but we don't have the skills to do that yet. Let's tackle number C, and I'm going to let you guys guide our understanding here. So C says x squared minus 29x plus 28. Just off the top of your head, do you think this one's going to work or not?
No.
Okay,
Probably.
what? Let's try it.
Can the x be squared? Like x squared minus 29x squared? Or no?
What would we do if it said x squared minus 29x squared?
Probably add them.
Yeah, we'd just add or subtract them because they're like terms. So we'd put them together.
Oh, so that would never happen.
So it would never happen. Might happen if it's a trick question, but then it would have one more step. You'd have to combine like terms and then do this. Okay, let's make our chart. We've got the sum and the product. S and P. Emma, what do we have a sum of? So we're going to have two numbers in our factors, and they're going to add to the coefficient of our x term. So we're going to have a sum of negative 29. Lindsay, what is our product? 28. So now we're looking for two numbers that have a product of 28 and a sum of negative 29. What's my next step, Jonathan?
Get the factors from 28.
Let's get all the factors of 28. We probably don't need all of them, but let's get a whole bunch of them. Let's use the strategy where you go up the mountain and back down the mountain. So let's start at 1, right? 1 and 28. And then while we're there, why not do negative 1, negative 28? Is 2 a factor of 28?
Yeah.
Who's his partner?
14.
14. And while we're there, let's do the negatives. Negative 2 and negative 14. Is 3 a factor of 28? No. Is 4?
Yes.
Yep. 4 and 7. Let's do the negative ones while we're there. Is 5 a factor? Is 6 a factor? Now we're at 7. So we've gone all the way up the mountain, and we already did all our ones going back down. So we're done. All right. Do any of these have a sum of negative 29?
Yes.
Negative 1, negative
Right there. So what does that tell us? That in factored form, the quadratic expression x squared minus 29x plus 28 is equal to x minus 1, x minus 28. I want to pause for a second on this one and just re-illustrate how to check it going backwards. We know that if we FOILed this, we'd have first times first, x squared. Then we'd have outside times outside and inside times inside, and both of them would result in having an x in them. So we're going to have negative 28x and negative 1x, and that adds to negative 29x. And then if we multiplied our last terms, negative 1 times negative 28, positive 28. So that's good. D. D says x squared plus 3x minus 18. X squared plus 3x minus 18. I'm going to let you go ahead and do the whole thing on your own from scratch. And then go ahead and check the board in a little bit once we are done. Double check to see how your list did. If you have all those factors, it's a little bit tougher because the product was a negative number, so each group has one negative number, one positive number. So you could do negative 1, positive 18, or positive 1, negative 18. And those are different now. So now you need to decide out of that list of factors, which pair adds to 3? Which pair has a sum of 3? 6 and negative 3.
And both. Isn't it the opposite?
No, then it's negative
This one would be 3 minus 6, right? Which would be negative 3.
Yeah.
Good call. So here we go. We can rewrite it as a product of two binomials. We have x minus 3 and x plus 6.
Wouldn't it be x minus 3?
Not
That's a very good
e.
question.
Let's do e quickly because we are running out of time. It's x squared minus 4x minus 21. And we have our sum in our product list. We're going to do the products of negative 21. They are 1 and 21, well, negative 1 and 21, or 1 and negative 21. Then we have 3 and negative 7, or negative 3 and positive 7. That's all of them. And they need a sum of negative 4. So which pair is it?
It's negative 7.
Yeah, the one with negative 7. Another way to think about it is like this. If the middle term, the coefficient, is negative, then the bigger number must be the negative number, right? The bigger value must be the negative one. So 7 must be negative. Go ahead and throw it in your factored form. X minus 7, x plus 3, and you're done.
Now I put it x minus 3 and x plus 7.
Don't do that.
Usually we put
Okay, example 2. Example 2 is to find the dimensions of a water garden. So you are given a rectangle, and you are told that the area can be represented by the trinomial x squared plus 5x plus 6. And earlier in this lesson, we learned that factoring is just like finding the length and the width of something. Well, the length and the width of something is called the dimensions. So here we're finding the dimensions of the water garden. So we want to determine binomials that will represent the dimensions of the rectangular water garden. So what do we need to do to this quadratic expression? We need to factor it, just like we've been doing. Sum, product. Tanner, we need a product of,
Positive 6.
and we need a sum of.
Positive 5.
Let's make a list. 1, 6, 2, 3. That's it. Now I could do my negatives. Negative 1, negative 6. Or negative 2, negative 3. And which one has a sum of 5?
2 and 3.
2 and 3. So x squared plus 5x plus 6 is x plus 2, x plus 3. And because it's a word problem, we need to represent our final answer in a sentence. The dimensions of the water garden can be represented by x plus 2 and x plus 3. So those are the dimensions, either length and width or width and length. It doesn't matter because multiplication is, we can switch the order of things. Okay, part B of example 2 asks us to find the actual dimensions if x is 1 meter. What do we have to do if we know that x is equal to 1 meter?
Sub it in, throw it.
Yeah, anywhere we see an x, we can sub it in. So here in factored form, we have x plus 2, x plus 3. So we're going to have 1 plus 2 times 1 plus 3, which is 3 times 4. 3 times 4 is? It's 12. So now we've multiplied, and now we're talking about area. So one of these lengths is 3 meters, and the other length is 4 meters. So what is the area measured in? Yeah, meters squared, or squared meters. Or 12 meters squared. And that's our final answer. Your homework is at the bottom of your page. Refer back to your examples. Some of the keys that we learned about was just sum and product. So if you cannot factor by pulling out a common factor and you cannot factor by grouping, then you try to factor by sum and product.
If it's